Good day, students. Today, our topic of discussion is X-ray diffraction using a Bragg's X-ray spectrometer. Now, in this instrument that was designed by the Bragg scientists, uh, we had a lot of components and they are listed here. So let's go through them. Now, this apparatus is used to study the crystal structure and the symmetry within that crystal. So this is the figure, and here in this figure we can see that we need X-rays from an X-ray tube. So that is our source, and these X-rays are then passed through two slits, S1 and S2. This is to make the X-ray beam into a narrow beam. Okay. So this narrow beam is then made to fall on our sample, that is our crystal. This crystal is placed on a turntable. That is, that table can be rotated 360 degrees. Okay. Now, on one side of the turntable, we have our detector. It can be a photographic plate or it can be an ionization chamber. Here in this figure, we have an ionization chamber that is used to detect these X-rays. Now, when X-rays fall on this sample, we are observing the reflection or the reflected beam from this sample. Hence, this sample or this crystal is acting as a grating. That is, it is acting as a reflection grating. Okay. If we were observing the diffracted beam passing through it, we would have been seeing the transmitted beam and it would have acted as a transmission grating. But here we are viewing the reflected beam, hence it acts as a reflection grating. Now this reflected diffraction beam, on the path that it passes through, we place an ionization chamber. So if the angle theta is varied, when this theta is varied, the angle of the sample is varied, at sometimes we may get a diffraction beam if it obeys the constructive interference conditions. We will get a diffraction beam at this position, and at other angles we won't get any diffraction beam. So only at some particular angles we get a beam that passes through this ionization chamber, and when this beam is passing through this ionization chamber, it causes a current to form in this circuit, and we measure that current. In this video we can see that. Just look through. So here we can see, by turning, we can see a peak at this angle. Again, turning the detector, we get another peak at this angle. Okay, so we get diffraction beams only at particular theta angles, and at that theta angles this crystal will be diffracting this X-rays from particular planes. Here in the D3 plane we are getting the third peak. So here we can see that the crystal, it shows a peak in this D1 plane. Then again in this D3 planes it shows another peak. Here, instead of the ionization chamber, we can also place a photographic film around this crystal. That is, a photographic plate can be placed surrounding the crystal. So here what happens is, when these X-rays fall on this crystal will be having several symmetric planes. Okay, so each plane will form diffracted beam in each particular theta angles. So you have different spots at different theta angles, and all these spots will be recorded on this photographic plate. Now here we will be observing this diffraction beam for each 2 theta angle. So let's see how this angle is recorded as 2 theta. Now if this is the axis of the beam, the sample, let it be at an angle theta. Okay, so this is the glancing angle, right? The angle between the incident beam and the surface of the sample is called the glancing angle theta. If this angle is theta, then the reflected beam will also be having an angle theta. Okay, so the angle between this surface and the reflected beam will be theta, and we have this total angle then to become this theta plus this theta, that is 2 theta. Okay, hence, while taking the plot, we measure the intensity of the diffracted beam with respect to the 2 theta angle of the detector. This is an example of the X-ray diffraction plot. Here, the intensity of the X-rays is plotted on the y-axis and the diffraction angle 2 theta is plotted on the x-axis. And this is the nature of the XRD plot that we get. Here, we have taken the XRD plot of a single substrate, a single sample at different temperatures. Different colors represent the XRD plot at different temperatures. Now, this is another XRD plot. Here, we have taken the XRD of titanium nitrate substrate under two different conditions, using a monochromator and without a monochromator. So we can have different conditions while taking an XRD plot, but always it is measuring the intensity of the X-rays versus 2 theta angle, and in that we will get a series of peaks, and by the location of these peaks we can understand from which planes these diffracted angles are, or these diffracted X-rays are obtained. We can identify the Miller indices of those peaks. Here, this peak corresponds to the diffraction beam from 111 plane of that sample. This peak corresponds to the diffraction beam from the 200 planes of that substrate. In XRD, we find these Miller indices of these planes and we find the complete set of Miller indices to finally understand the structure of that particular crystal. Now let us see the particular case in sodium chloride. For NaCl crystals, we obtained the XRD plot, and in that we saw that the first order diffraction maxima was obtained at 5.9 degree, 8.4 degree and 5.2 degree for these respective 100 plane, 110 plane and 111 planes. Now according to Bragg equation, we have n lambda is equal to 2d sine theta, where n is the order of diffraction, lambda is the wavelength of the source light, d is the interplanar spacing between the atoms in the crystal, and theta is the angle of glancing angle. From this we understand that d is proportional to 1 by sine theta. Using this relation, we are going to write d100 proportional to d110 proportional to d111 is equal to 1 by sine theta 1 proportional to 1 by sine theta 2 proportional to 1 by sine theta 3. Substituting the angles, we get it like that. And by calculating this, we get this proportionality ratio to be in terms of 9.73 proportional to 6.84 proportional to 11.04. Now usually while taking the ratio, we make one of these terms into one. So let us make 9.73 term as 1. So for that we divide all the 3 by 9.73 and hence we get this ratio 1 is to 0.703 is to 1.14. Now this can be rewritten as 1 is to 1 by root 2 is to 2 by root 3. Now these figures, they remind us of something. Okay? If we calculate the interplanar spacing DHKL for a cubic crystal having unit lattice parameter, that is the lattice parameter A is 1, we get D100 as 1, D110 as 1 by root 2 and D111 as 1 by root 3. Here we see that the D111 value is given as 2 by root 3. Hence, it is not a simple cubic structure. We identify this to be as a face-centered cubic structure. So by finding out the relation between these D values, we can come to a picture of this structure of this crystal. Now, XRD is usually done in two ways. One of the ways is the powder crystal method. Here, the sample or the crystal that we have taken is powdered. We make it into smaller grains. Even though we are grinding it, we are not taking a fine powder, we are just coarsely grinding it. If we take a coarse powder, there will still be crystals of that sample, smaller crystals of that sample. So while we take the XRD or the X-ray diffraction from that sample, while X-rays are falling on that crystal, at the same time we get peaks at different theta positions. Because light or this X-rays are falling on different planes, different atomic planes simultaneously, and different Bragg reflections are obtained at the same time. So at this point, in the diffraction of the X-ray, we get the spot due to this incident X-ray beam. Now, when we place a photographic film on this circular region, we can measure or we can take the plot of these diffraction beams. We can read the diffraction pattern. Now, this method is called the Debye-Scherrer method. Here, the sample is taken in the powder form and the diffracted rays will be on the surface of a cone. Okay. You can see that the diffracted beams that is falling in this angle, it will be falling on the surface of this cone, and the sample is in the vertex of this cone, and on the base we will be having the photographic film, and on the edges of this film we will get the recording of the diffraction beam. Now the angle, the semi-vertical angle of this cone is 2 theta. Okay, it is not theta, it is 2 theta. Here, the wavelength is fixed. Okay, so the wavelength of the X-ray beam is fixed, and diffracted beams at various theta angles is obtained at the same time. Infinite orientations are obtained at once. At that particular instant, we get different orientations. Now, the picture of this cone is drawn a bit more clearer. Here we can see that the semi-vertical angle 2 theta, it will be equal to this radius divided by the distance towards the photographic film from the sample L. Okay, so by measuring the L distance from the sample towards the film, and by measuring the distance of these diffraction beams from the center of the photographic film, we can take a measure of 2 theta angles. And hence the plot is drawn. Now this is a picture of the camera that is used to take this pattern. This is called the Debye-Scherrer camera. Okay? And inside this, the photographic film is placed, and on this film the different beams are recorded. In this film we can see that the beams are recorded at different maxima positions. This is a picture, and on the right side we get the image of the photographic film from this Debye-Scherrer camera. Now the next method is the rotating crystal method. It is again called the Laue method. Here the X-ray beam is fixed, but the sample is continuously rotated. Okay, the sample is rotated. The detector is not rotated here. The detector is fixed, but the sample is continuously rotated. And while the sample is rotated, we get different spots emerging from it, and these spots can be measured either on a photographic plate as shown here or in a ionization chamber. Now let us just try to differentiate between reflection and diffraction. Here, reflection can be seen as the bouncing of the wave from the surface of a substance, right? It occurs from the surface of a substance, whereas diffraction occurs throughout the bulk of that material. Here, X-rays are penetrating into the material and they are getting diffracted from each atomic planes. So they are penetrating into that material. Reflection can take place at any angle, but the X-ray diffraction can take place only at Bragg angle. Only if it obeys the conditions of constructive interference will it undergo diffraction. Reflection can be obtained 100%, that is, all of the light can be reflected. But in diffraction, only a small fraction of that light is diffracted. Only a small fraction of these X-rays are diffracted. Now, from the data that we get from these XRD plots, we use it to identify the material, to identify this mineral or what substance it is, what element it is, what sort of composition it is. And also we can determine the dimensions of that unit cell. We can determine the Miller indices of that structure, and from that we understand its atomic spacing, D's, and then we understand its bond strengths, the bond length and its bond strengths. Finally, from that we come to a conclusion of the structure of that material. XRD has been helpful in a lot of ways for researchers to develop. This is one of the non-destructive techniques. In the rotating crystal method, we take the crystal itself to study it, and it can be used as a non-destructive testing method. That's all for today. Thank you.